Hi, in this class, we're gonna look at the new section, light and optics. Uh, Light is an interesting thing that uh, exists everywhere. You're looking at the light right now, but it's known that light can be viewed, treated in two ways. And the first, we're gonna look at the perspective of waves, as a waves. The second approach to look at the light is the product particles. But we learned that in the previous section that the light is just a small portion of the, a broad electromagnetic waves, right? So this is the continuation of the previous section. So there's a smooth transition between the previous section and today's lecture. And we're also going to look at the properties of light, such as transparency, colors, and various other phenomena associated with the light, especially the refraction. The light is known to travel at a different speed in a different medium, different matter, because of of the way the electromagnetic waves interact with the electrons or inside the atoms, and well, that's how the bending of light occurs, and as a result, we have things like dispersion, total internal refractions, how rainbows are formed. Those things can be explained by this phenomenon. And then atmospheric scattering, how atmosphere interacts with the light. Light can be either absorbed or rescattered, re-emitted by the atmospheric molecules. So that's why the skies appears to be blue during the day. It's not because the air itself is blue, but it's the light coming from the sun. A certain portion of the light is scattered away, while other portions are, traveling straight. And that's why blue sky or red sunsets occur. And we're going to look at those. And you saw that within the visible range, there's a rainbow of colors, right? Well, we're going to define colors in the later slides. So this is what I just talked about. The speed of light is the fixed number, which is this much. And this is the maximum speed that anything can travel. But it's known that the light travels at the lower speed inside the other materials, like glass or water or air, right? Because it's not vacuum, it's made out of stuff, matter. Right? So how does light travel through those, matter, different matter? Well, that will be explained later, but it's known that each medium or matter has specific optical characteristic, and it's specified by this number called index of refraction. Index of refraction, that's the rate of the at which the light travel in the medium with respect to the vacuum, right? And apparently this n has to be greater than 1 because this index of refraction is relative. It's a ratio between the speed of light in the vacuum and that of in the certain medium. So it's a ratio, right? And because we set the speed of light in the vacuum to be 1, this number n has to be less than, is always greater than 1. And these are the typical indices of refraction for the various medium. Air is very close to the vacuum because it's very, sparse material, right? Compared to water or glass, denser material has higher index of refraction, as you can see. And you see that the diamond has as much as 2.42, the index of refraction 2.4. So it means that it travels, less than half the speed of light in the vacuum. Right? So this much. That the light travels very slowly, less than 50% inside the diamond. And the reason why denser material, transparent material, let the light travel slower is because the material is made out of atoms, right? And atoms, it's densely packed in those like diamonds or water or ice, right? And when the light enters those transparent medium, electrons inside the atom, or each atom vibrates because of you remember the light has electric component, right? So that has an effect of shaking an electron inside of matter, but right. So it shakes the electron up and down, but the electron has a slight mass, right? It's a small mass. It has a small mass. Because of that, it has a little bit of latency to respond to this oscillation, external oscillation. Therefore, there's a time lag between the absorption of the light by the electrons and the re-emission of the wave by those oscillated electrons. So that makes the light travel slower inside the matter. Right. And it's also known that the wavelength of the light re-emitted by the electrons in the transparent material is a shorter, slightly shorter wavelength, resulting in slowing down of the light inside the transparent material. And some matter is transparent, like glass or diamond or water, but other material like plastic or ceramic, they're opaque, right? They don't let the light travel through the material, because the energy, the electrons pass the energy to the nearby atoms, so this re-emission of the wave, it doesn't occur inside an opaque material. Right. So as I said, this slight delay due to the mass of the electrons causes the delay and slowing down the light. Therefore, light travels more slowly in the denser material where there's more electrons packed in. Well, light consists of many, or electromagnetic waves consists of many, comes in many frequencies or wavelengths, right? And the matter responds to the electromagnetic wave differently depending on the wavelength of the incoming light. For example, in glass is known to shield, absorb the ultraviolet. Yeah, so ultraviolet it's blocked by the glass. While visible light, well, everyone knows from the window, by looking at the window, it's a glass let it pass. Right? So glass has this optical characteristic that it's like a filter that let only visible light pass, while the ultraviolet and infrared components are blocked. While blocked, or absorbed, or reflected, to be exact. And well, light, as in conventional sense, means the visible component of the light, something that our eyes can perceive. But there's a whole range of invisible portion of the electromagnetic components, and using the proper instrument, we're able to visualize those invisible light, that's generated in different parts of the galaxy, for example, or other parts of the universe. Yeah, that's how the astronomers detects the existence of the black hole, or pulsars, or some other interesting characteristics, by looking at the same celestial object at different wavelength. Right, this is what the Milky Way looks like in the visible light, but in X-ray, yeah, the same galaxy looks like this, totally different. So by looking at by the different wavelength, we can see the distribution of the different matters. Especially in the infrared light, the band, you can see the clear bulge of the Milky Way, while that is blocked in the visible light, because you can see it's not as pronounced as the infrared picture, right? Right. So by using many different wavelengths of the light, we can observe the cycle of star, gas, star, reincarnation of the stars in the Milky Way. And color uh, is this is a visible component of the light, and you can break down the light into these. When you break up the white light, it comes in this rainbow uh, colors. Many different colors are mixed in the white color, right? And the white color consists of many different colors: your red, orange, green, blue, violet. You know, the bluer it gets, the shorter the wavelength is, and the redder the light is, the longer the wavelength becomes. And be careful, this scale gets smaller, the wavelength gets shorter as you go toward the right. So what is the color of the light? The color corresponds to the frequency of the light, or the wavelength of the light. You know, you remember the frequency and the wavelength are inversely proportional, right? And any colors can be created by combining three primary colors: red color, green color, and blue color, right? As you can see in this picture, right? That's how the LCD screen generates all colors using three diodes, three LEDs, three colors, the RGB, right? So there actually is no white color, no white light. White light doesn't exist, actually. White color is a mixture of all these three elementary colors. Right. So by adjusting the ratio of these three elementary colors, you can produce full color images. And it looks like, the blue color is cooler, seems cooler than the red color. Red color appears to be warmer, right? But that's just the physiological effect. In actuality, blue color is hotter. Next topic is about bending of light. That's caused actually by the change in the light speed inside the different medium, right? And the amount of bending that occurs depends on the difference in index of refraction between two matters. This bending occurs when the light hits the interface between two matters. And this difference causes the bending of the light. Well, light is produced by the luminous body because of the quantum mechanical effect that will be discussed in the later chapter, but the typical example is the sun. Sun is emitting light through the thermal energy, right? Where does this thermal energy come from? It comes from the fusion reaction happening at the core of the sun. And that's transmitted through the body of the sun, and it escapes from the surface and radiating away. Right. While you can see that the sun is very bright, you can also see the moon moon itself doesn't emit this light. You're able to see the moon, but when you do the spectroscopy on the moon's light coming from the moon, it actually the same as the light, the, the spectroscopy of the solar light, solar rays, because you're seeing the reflected light coming, the solar rays reflected on the sun, the moon, on the moon's surface toward the Earth. That's what you're seeing. So you're indirectly seeing the sun when looking at the moon. Right. So when you strike a laser beam at the water with some angle, this angle is known as incident angle. Okay, incident ray. You can see in this picture that this ray splits into two paths at the interface between air and then water. Right. So this light is, portion of the light is reflected back into the air, while the majority of the light, you can see that it bends inwards and enters the water. And this angle, as you can see, is theta 2 with respect to the normal line is smaller geometrically than the instant light, instant angle, theta 1. That's because the water has a greater index of refraction than air. Another interesting thing, though, in the optics is that the reflected angle, this theta, is always the same as the incident angle. When you change this incident angle, so does the reflected angle. And, well, theta 2, the refracted angle also changes, but this angle is always smaller in the case of water and air. Right. So water has the index of refraction about 1.33, while glass has higher index of refraction. So what does this mean? It means that the refraction angle is stronger for the glass because n is greater. So it bends at the interface, at the surface of the glass more strongly, bends more inward than water. Right. Well, this refraction doesn't happen when the ray hits the interface at the right angle. What happens in this case is only the shortening of the wavelength. Why does this happen? Well, I explained that it's because of the delay of the re-emission of the light due to the inertia of the electrons. Right. Well, when you shed light into the water, it's always the refracted rays bent towards the normal. But what about this case when you know, if the light source is located in the water, what would happen? Where does this ray travel? In the air. In this case, something opposite happens. It bends because the air has smaller index of refraction. The ray is bent away from the normal. Right. And here is the like a magic. It's not really magic, but it looks like a magic due to the index of refraction.
The index of refraction of a material is a measure of how fast light travels in a material. If light goes from one material to another and the two materials have different indices of refraction, the light is bent. But if the two indices of refraction are not very different, the light does not bend too much. We will now conduct an experiment to understand the index of refraction. Here we have two glass beakers, one small and one big, and some vegetable oil. Put the small beaker inside the big beaker. You can see the small beaker is still visible. Now pour the oil inside the small beaker. Keep pouring it so that the oil can overflow into the bigger beaker. As soon as the big beaker is filled with oil, you see, you cannot see the small beaker through it. The small beaker has just vanished. The small beaker has almost the same index of refraction as oil. So light that is traveling through the beaker into your eye is not bending at the surface of the glass. Therefore, you cannot see the small beaker. The index of refraction of a material is a measure of how fast light travels in a material. If light goes from one material to another and the two materials have different indices of refraction, the light is bent. But if the two indices of refraction are not very different, the light does not bend too much. We will now conduct an experiment to understand the index of refraction. Here we have two glass beakers, one small and one big, and some vegetable oil. Put the small beaker inside the big beaker. You can see the small beaker is still visible. Now pour the oil inside the small beaker. Keep pouring it so that the oil can overflow into the bigger beaker. As soon as the big beaker is filled with oil, you see, you cannot see the small beaker through it. The small beaker has just vanished. The small beaker has almost the same index of refraction as oil. So light that is traveling through the beaker into your eye is not bending at the surface of the glass. Therefore, you cannot see the small beaker.
Right. So that was the demonstration of how index of refraction can do this kind of optical magic. Right. So the bending doesn't occur very much in the oil. So that's why the beaker inside the beaker disappears, seems to disappear. Right. And the effects, there are various effects caused by this refraction cases. That well, I'll explain what the total internal refraction reflection later. It's used in the fiber optics, and you can see through a window, but or dispersion, this refraction actually, the way the light bends differs depending on the wavelength of the incident light, and that causes the dispersion. The, the shorter wave is bent more strongly than the longer wavelength light. So that creates the spread of light. And that's used in the prism or rain. That's how rainbow occurs. So this is why when you see the straw that's inserted in the water, it seems to be bent at the inside the water. Or if you look at your leg, you know, in the on the pool, your leg seems to be crooked, right? But it's not because your leg is broken. It's just that the light, that's entering the water is bent actually twice. That's why it's bent harder. So that's why it looks it looks doesn't look straight. So when you do fishing, the same thing happens, that a fish swimming at a certain depth, the light is striking on the surface of the fish and then reflected towards the surface of the water, but the refraction occurs at at when exiting the water and entering your eye, right? And that's when the light is bent away, right? So it appears that your the fish that you're trying to catch seems to be swimming shallower than it actually is. Right. The apparent location of the fish seems closer to the surface. So that's how the careful, the brilliant cut is made. And another device that uses the total internal reflection is the fiber optics. Fiber optics uses the glass, right? The long tube of glass that which sends the light. But inside this cable, we don't want the light to leak at every time it hits the internal wall of the fiber optics, right? Well, it's this fiber optics is carefully designed such that every time it strikes the internal wall, the total internal reflection occurs, so the light doesn't leak out into the outside the cable. So that can, in that way, we use laser beam to send the information through the optical fiber, but that light can travel over long distance without much attenuation, without much dissipation or loss of energy, right? And the optical fiber ensures the stable condition, that's not interfered by the atmosphere or corrosion, or very stable and reliable uh, data communication is achieved thanks to the fiber optics. Right. A copper can carry only 32 telephone calls, while optical fibers can handle 10 1,000 times greater than that. Right? So there's a lot of benefits and advantages of using fiber optics communications, and nowadays that's uh, the main uh, data transmission method in Japan. Right? And well, it's still a little bit more expensive than you know uh, the copper cable, but it's getting because of the industrial development. Yeah, this downside is getting uh, fixed. It's getting less expensive and readily available now. Okay, that's it for today. Thank you.